All right, so we have a hypothetical reaction, AZ plus B minus goes to AB plus Z minus, and we've explored something about the thermodynamics for that reaction and something about the kinetics of that reaction. We're ready to draw a reaction energy diagram. So in our reaction energy diagram, we're going to have reaction progress on one axis. You may have called that the reaction coordinate, that's fine. And then energy increasing on another axis, maybe that's G, free energy, maybe. So we're ready to draw a reaction energy diagram. So from thermodynamics, we said, hey, we can figure out whether or not this is favorable or unfavorable. Well, let's just imagine that it's favorable. And that is delta G for the reaction is less than 0. It's negative, right? So that's a favorable reaction. The equilibrium constant is greater than 1, we would say. All right, so we're ready already to say something on our reaction energy diagram. What we're saying is that the starting materials are at some energy, whatever that is, and the products are at another energy, whatever that is. And the products are at a lower energy, this is downhill, than the starting materials. So my starting materials are here somewhere on my reaction energy diagram, and so that's AZ plus B minus, and over here I have AB plus Z minus. All right, and so what about our kinetic contribution? So remember, from kinetics we saw that our mechanism is likely to be a two-step mechanism. And so in this two-step mechanism, we have a slow step, the rate-determining step, and a fast step. And because we have a slow step and a fast step, these two steps together, they add up to the overall reaction. And so we had a slow step, the rate-determining step. We said, hey, then this is the rate equation, AZ raised to the first power. And, contribution from B minus, the exponent for that was 0. It's not involved in the rate-determining step, the slow step. So remember, that's equivalent, saying that it's dependent upon the rate constant times the concentration of AZ raised to the first power. So we got one step that's slow, that's the rate-determining step, and one step that's fast. Well, if we think about this again, this is going to be hard to do uphill, and this is going to be easy to do downhill. So at some point in the middle, we are at an intermediate. So this is an intermediate stage. And the intermediate stage contains the products, say, of the first step and what remains of the reactants. So that's A plus B minus plus Z minus. That's our intermediate stage. Now in the first step, we have a bond that's breaking. So that means that in between each of these two stages, we have a bond that's in the process of being broken, a partial bond. And at some point in that process, I have an energetic maximum that is above the energy of my intermediates. And if AZ is breaking, it's now a partial bond. A becomes positive, so at this stage it has a partial positive, and Z is becoming minus, so it has a partial minus. This is called a transition state. Maybe you called it an activated complex in general chemistry. I'm going to call it a transition state. And so this is transition state 1 for the first step. The second step likewise has a transition state, but it's fast. And so this transition state 2, is lower in energy than the energy of the first transition state. And of course, it also has some partial bonds. Bonds are being formed, or a bond is being formed in this step. So we now have a partial bond between A and B. B starts out minus, so it's becoming partial minus, or it is partial minus. And A started out plus in this step, so now it's partial plus. So now we have our reaction energy diagram that communicates to us all of the information that we got from kinetics and thermodynamics. There is some nomenclature. This distance here, that's delta G dagger, right? That's the activation energy, maybe you called it. This energy difference right here, That's delta G for the reaction. What we decided was less than 0. This is also an activation energy, but it's not for the rate determining step. So our one reaction energy diagram tells us everything that we knew from our thermodynamics and kinetics. And if we have this reaction energy diagram, then we know this information. Likewise, if we have this information, then we know that something like this must be the reaction energy diagram.